Hi all. Today we discuss invertible linear transformations. To define invertible linear transformation, we define one-one transformation and onto transformation. So a linear transformation T is 1-1. Obviously, T is transformation from V to W. It is said to be 1-1. Uh, if T alpha equal to T beta implies alpha equal to beta. This is the definition of one-oneness. That means distinct elements have distinct images. This is the required condition for one-oneness. And onto map, T is onto if T is onto if the range of T is uh, all of W. The range of T should be constant with W. Range of T is denoted by RT, that should be W if T is a linear transformation from V to W. Or in the other way, we can define every element of W has an inverse image in V. So this is the definition for ontoness. Then you can define invertible linear transformation. If T is from V to W is a linear transformation which is uh, 1-1 and onto, then T is called an invertible linear transformation. Invertible linear transformation. This is the definition. In this case, you can define a inverse map from W to V as well. Okay. Then we will prove that this T inverse is also a linear transformation from W to V. Okay, obviously, T is 1-1. If T is 1-1 and onto, we can define T inverse such that T composition T inverse, that is T inverse equal to T inverse T, that is equal to identity map. This is the required condition for invertible functions. So if T is linear transformation and with 1-1 and onto, we can get T inverse as a map from W to V with this condition, and we will prove that this T inverse is also a linear transformation. Okay, how will you define T inverse? T inverse of something beta is equal to alpha if and only if T alpha is equal to beta. This is the definition of T inverse. So we will prove that this T inverse is a linear transformation from W to V. How will you prove this? T inverse of C beta 1 plus beta 2 is equal to C times T inverse of beta 1 plus T inverse of beta 2. We need to prove this. This is our claim. So we start with this T inverse of this. If beta 1, this has to be proved by taking beta 1 and beta 2 from W. If beta 1 and beta 2 are elements of W, we can say that since this T is onto, there exists alpha 1 such that T alpha 1 is equal to beta 1 and T alpha 2 is equal to beta 2. Okay, there are alpha 1 and alpha 2 belongs to V. Now, what is C beta 1 plus beta 2? By definition of the sum, you can write it as C times T alpha 1 plus T alpha 2, that is equal to T of C alpha 1 plus alpha 2. Since T is a linear transformation, then this shows that T inverse of C beta 1 plus beta 2 equal to inverse image of this is equal to C alpha 1 plus alpha 2. That means T inverse of C beta 1 plus beta 2 is equal to C alpha 1 plus alpha 2. Now, what is alpha 1? Alpha 1 is nothing but T inverse of beta, right? T inverse of beta 1, and what is alpha 2? From this you can write alpha 2 is T inverse of beta 2. So that is T inverse of beta 2. So this shows that T inverse of C beta 1 plus beta 2 is equal to C times T inverse of beta 1 plus T inverse of beta 2. So this shows that this T inverse is not only a map from W to V, it's a linear transformation from W to V. So T is invertible if and only if there exists a linear transformation T inverse with this condition. Okay, more than a function, this T inverse satisfies the condition for linear transformation. So this is referred as theorem 7 in the textbook. So this proves theorem 7. This is the proof of theorem 7. So this is very important theorem. Now we have a definition: non-singular linear transformation. Linear transformation. So the definition is, if T is a linear transformation from V to W with the condition T gamma is equal to 0 implies gamma is equal to 0, then T is called non-singular linear transformation. So this is the definition. What do you mean by this? Whenever gamma is mapped to 0, then the only possibility for this gamma is 0. Okay. So what is the consequence of this? When you consider, this is V, when you consider this this statement, T gamma is equal to 0 implies, this immediately implies that this gamma is a member of, this is if and only if gamma is a member of null space of T, right? Null space of T. Then this statement implies that gamma belongs to null space of T, implies gamma is equal to 0. Okay, that means null space of T is singleton set 0. That is the meaning of this. So whenever null space of T is equal to singleton set 0, we can say that this T is, the corresponding T is a non-singular linear transformation. Okay, so in the case of linear transformation, the non-singularity and one-oneness are equivalent. Okay, that means if we assume T is 1,1, we have whenever T alpha is equal to T beta implies alpha equal to beta. So using this condition, you can prove that T gamma is equal to 0 implies this gamma is equal to 0, because T gamma equal to 0 implies T gamma is equal to 0 equal to T of 0, because for any linear transformation T of 0 equal to 0. Using the one-oneness, you can get gamma is equal to 0. So when you assume this, implies that this statement, okay, that is T is not singular. So T is 1,1, implies T is non-singular. Okay, similarly, when you assume T is non-singular, that is T gamma equal to 0 implies gamma equal to 0, then you can easily prove that T are the one-oneness of T, because T alpha is equal to T beta implies T of alpha minus beta equal to 0. By taking this T beta to the left, then T alpha minus T beta equal to 0. This implies T of alpha minus beta equal to 0 implies alpha minus beta equal to 0, because the non-singularity T gamma equal to 0 implies gamma equal to 0. This is the hypothesis. So alpha minus beta equal to 0 implies alpha equal to beta. This shows that T alpha equal to T beta implies alpha equal to beta. That means the non-singularity implies the one-oneness. So this shows that T is 1,1 if and only if T is non-singular. Okay. Now we have an interesting consequence of this non-singularity, that is referred as theorem 8. let T be a linear transformation from V into W. Then T is non-singular if and only if T carries each linearly independent subset of V onto a linearly independent subset of W. That is, if you consider T is from anyway, V to W, and T is non-singular, that means T gamma equal to 0 implies gamma equal to 0. Now this is statement 1, and what is statement 2? T carries linearly independent set to linearly independent. That means if W1 etc. Wk is a linearly independent subset of V, then the image set T carries these alpha 1, alpha 2, etc. alpha k to another linearly independent subset in W. Okay, that means T1, this alpha 1, alpha 2, alpha k is linearly independent, then the image set is also linearly independent in W. Okay, this is linearly independent W. So we need to prove that 1 implies 2 and 2 implies 1. So we prove 1 implies 2 first. So we assume this T gamma equals 0 when T gamma equals 0 and plus gamma equals 0, and we need to prove that the linearly independence of this set by assuming the linearly independence. Here we take C1 T alpha 1 plus etc. Ck T alpha k equal to 0. We will prove that each Ci is equal to 0. So to prove this, we consider this as P of C1 alpha 1 plus etc. Ck alpha k equal to 0, since T is a linear transformation. But we have assumed that 1 T gamma equal to 0 implies gamma equal to 0. So this implies this by taking this as gamma, we can say that C1 alpha 1 plus etc. Ck alpha k equal to 0. Consequently, these are linearly independent. Set alpha, say alpha 1, alpha 2, alpha k, we can get C1 equal to C2 equal to etc. equal to Ck equal to 0. This proves 1 implies 2. Now we will prove 2 implies 1. To prove 1, we need to prove the contrapositive of this. For this theorem, we will prove that whenever, what is the contrapositive of this? Gamma not equal to 0 implies T gamma not equal to 0. So this is obvious, because when you take gamma not equal to 0, then the set singleton set gamma is linearly independent set in V, but our assumption is 2. T carries every linear independent set to independent set. So if gamma is linearly independent, then by 2 you can say that the set T gamma is linearly independent set in W. Consequently, you can get T gamma not equal to 0. Since the set containing 0 is always linearly dependent, so T gamma is linearly independent implies T gamma not equal to 0. So we have gamma not equal to 0 implies T gamma not equal to 0. This shows that T is non-singular. Okay, that means this is a characterization for non-singular linear transformation or one-one linear transformation. Every one-one linear transformation or non-singular linear transformation carries linearly independent set to linearly independent set in W.